So another type of motion, we've talked about linear motion, we've talked about circular motion, and now we're leading into oscillatory motion. For these notes, we're going to talk about what oscillations are, talk about Hooke's law, which is for objects that are oscillating or moving back and forth. Have an example problem, introduce period and frequency, and show you a quick example for period and frequency. So oscillations are basically movements of objects that move back and forth between two positions. So you're familiar with waves. Musical instrument strings oscillate, swing sets oscillate. They involve force and energy. It takes force to make something move, energy to make something move. And oscillations actually can create waves. So the oscillating string on the guitar creates a sound wave. Okay, so we have Hooke's law. And Hooke's law is used to describe how forces interact with objects that oscillate. So in order to cause an oscillation, to cause an object to move back and forth, there must be a force. And the force that causes the object to return to its original position is called a restoring force. So let's say you think about a spring. You use something to stretch the spring, and the force that brings it back is the restoring force. The restoring force is measured in newtons, and the spring constant is representative of the strength of the spring, and it's going to be in Newton meters. And we have a displacement measurement from the equilibrium position. So the unstretched, relaxed spring would be the equilibrium position, and then how far you stretch it is the displacement. So here's a quick example. You have a mass hung from a spring, has a force constant of 1200 newtons per meter. The spring stretches 15 centimeters, and the question is, what's the value of the mass? So first, we need to find how much force is causing the spring to stretch. And then we can use the idea that force is weight and find the mass. So we don't know the mass, but we do know how far it's stretched. We need to make sure we're in the right units, so we want to change that 15 centimeters to 0.15 meters, and we do have a force constant. We use Hooke's law, which is force is minus kx, and our force is going to be equal to minus 1200 newtons per meter times that 0.15 meters, and that's going to equal negative 180 newtons. And then we plug that in to our force equation, and we have 180 newtons divided by a negative 9.8 meters per second is going to give us 18 kilograms. Oscillatory motion is going to have a period. And so it's periodic motion. It's motion that repeats itself back and forth over and over again. The period is the amount of time it takes for one complete oscillation. So it starts at a spot, moves, comes back to that same spot, however long that took. That's one period. It's measured in seconds. And then if you want to kind of flip that over, which is what the equation does, you want to know how many oscillations happen in a time period. You count the oscillations for a minute, and you would get so many per minute. Change that to seconds, and you have something called hertz, and hertz are cycles per second. So the equation or the relationship between frequency and period is they're inversely proportional. So frequency is 1 over the period. And just a real quick example, find the frequency of a tuning fork that oscillates once every 2.5 milliseconds. Now remember, sometimes those periods are going to be tiny, so we need it in seconds. So we have to change milliseconds to seconds, do the math, and we end up with 400 hertz. Alrighty, bye-bye.